Hello everyone, and welcome to the first part of this three-part SmallSat series, where we will be covering orbit design, solar and power design, and communication design. My name is Nova Cosme, and I'll be leading you in this SmallSat series. Before I dive into this lesson, I want to give a quick introduction to AGI and SDK. AGI is headquartered in Exton, Pennsylvania, and it is the creator of SDK, the industry standard analysis and visualization software for aerospace, defense, and intelligence communities. AGI was founded in 1989, and our background is in the development application for space systems. But since our founding in the last 30 years, we've greatly expanded to additional areas of interest, and we now cover aircraft and UAV systems, communication and radar, missile defense, and much more. In the SmallSat series, we will be using SDK, the industry standard 2D and 3D modeling for land, sea, air, and space-based systems. We can model all the capabilities that you see on my screen right now into one integrated tool. So SDK allows you to model your systems, simulate events, analyze the mission, and convey the results with its spatial geometry engine. It lets you do things like time dynamic, position, and attitude. So where am I now? Where will I be? And the orientation. Helps you understand the relationship among your assets in different areas. So who can I see? Who can see me? And can all my assets see each other? And then also analyze the quality of the relationship. So is my system too close? What's my signal to noise? And things like when is the sun going to be affecting my setup. For our lab, we will be focusing in on the space and communications aspects of this tool. And just to reiterate, this lab was originally written for MATLAB, but in today's session we will be using Analyzer Analyzer is AGI's trade study analysis tool. It lets you understand the design space of your system and gives you post-processing capabilities. If you haven't downloaded and installed Analyzer, please do so now. You can get that, they can send the link to you, but it's, so just like message in if you want to download the tool. Otherwise, you can sit back and watch me analyze this mission as though it were a demo. And if you're curious, if you'd like to see the MATLAB approach, you can check out the recording for our previous SmallSat series on the AGI FAQ page. But like I said, for this series and for this session, we will be using Analyzer. What we'll do is we'll use it to design the ideal orbit for our mission. And this lab also assumes that users have some general knowledge of SDK and know how to interact with the software. So that aspect of the tool I'm not going to necessarily focus in on. This series will primarily explore the project definition phase of a mission design, and it is broken out into three parts. And you'll see as we go through this that each part will build upon the previous lesson. And don't worry, AGI, we will provide any necessary files that you might need. The general mission of this entire series is to design, develop, implement, and launch a 1U Cubesat in order to characterize smoke fumes of active volcanoes in the United States. So we'll have a satellite flying overhead that's taking images of smoke fumes of active volcanoes, and then we'll analyze the solar and power of the Cubesat itself, and then analyze the information that will be downlinked to various ground stations. So just to reiterate, we want to make sure that in our setup and in our build that we have a satellite that maintains some orbit requirements and will maximize its orbit over some volcano sites. We'll be using SDK's tool Analyzer to optimize our orbit. In the next session, we want to make sure that our system can generate and store the required amount of power in order to continuously operate in its orbit, and it also must maintain a meter pointing to the imager to capture the active volcanoes that are on the ground. And then finally, the system must communicate with a ground station via ultra high frequencies and high frequency bands. So these are the high-level requirements, and we'll break down each one to model and analyze it in SDK throughout the series. Today, we'll be focusing in on the orbit design portion of the Cubesat mission. And our mission is to provide early indications of volcanic eruptions in the United States by observing steam emissions, airborne ash, and new lava flows. These observations will aid with current existing volcanic detection systems to save lives in the event of an eruption. So on our SDK satellite, we will have a payload. For simplifying our mission right now, we'll just use a simple satellite or a simple sensor, but the idea will be that our payload will utilize a revolutionary panchromatic and multispectral imager, which will fit within a 0.25U. This imager can provide approximately a 15-meter resolution at a 400-kilometer altitude, and with this imager, SDK satellite will be able to observe the steam, ash, and lava necessary to provide early warning signs of an eruption. A little background on our Cubesat. They are often secondary payloads on our launch vehicles, which is going to really restrict the orbit selection as they are often deployed into LEO orbits. So therefore, when we're designing our ideal orbit, we just have to take into account a couple parameters. So we still want to maximize the possible duration, maximize the time we can observe the volcanoes on the ground, but we have to take some conditions into effect. So we'll be constraining our Cubesat to a 0 to 90-degree inclination, and our altitude must be between 250 and 550 kilometers, or, we'll do this in SDK, so you'll see that that'll be 6,628 kilometers or 6,928 kilometers. And our imager will fit within a 0.25U and provide a 15-meter resolution at the 400-kilometer altitude. And the way we'll be modeling this is that we are going to simplify our orbit, and we're going to ignore solar radiation pressures, atmospheric effects, lunar gravitational effects, and higher Earth order obliqueness effects. However, because this is all done in SDK, once we have derived our final orbit, we can always add those conditions back in. Now that we know the scope of our mission, let's get started. I'm going to begin by opening up a starter scenario. So this starter scenario is located in the SDF. So if you haven't already, please open up a new instance of SDK. And when you get to the Welcome to SDK window, hit the Open a Scenario button. And you'll be able to explore and load in a pre-existing scenario. So you can find this scenario in a couple different ways. One, you can use the Browse feature and browse to the file location. So it's in this path here. I have it up on a slide, so I can pull that up and show you guys in just a moment. Alternatively, if you just wanted to search for it, you could certainly do that as well. So if you wanted to use the search option, which can be easier, you can just search for terms. So if I actually just search for starter, I'll be searching through the SDF. And in case you're not familiar with what the SDF is, it is the SDK Data Federate. It is it's a collaboration tool, so you can save and upload your SDK scenarios if you wanted to, save a mission that you've created and have somebody else be able to access it and work on it. The SDF would be the tool for you. All right, so I searched the term starter, and I'm going to open up a scenario called Small Sat Lab 1 Starter. So this is the one we'll be using to begin our mission. And in case you wanted to navigate to it from the SDF, I'm going to leave this slide up just to show you guys where the path is located. So it's going to be underneath Sites, AGI, Document Library, STK11, Starter Tutorials, and then this is the SmallSat Lab 1 starter.vdf. So of course you can navigate to it from here just by browsing, or you can just search for the term starter in order to open it up. Now that I have the scenario opened up, I'm going to have us, we can save our scenario, so that's always the first thing you should do. You can either save it to your desktop, so I'll show you guys how you can go through that, or you can actually save it back to the SDF. And we actually have a specific location for this training that you can go ahead and save your scenarios to. So the first method, if we wanted to save it to our desktops, I could go to File and then Save As. And this file format right now is a VDF, so that's a visual data format. So that's when everything is packaged up into one directory. And now the other method that you can use to save to is saving it as a scenario. All right, so if you go into the Save As, and if you wanted to save it to the SDF, the file location that we're going to have everybody load their files to, here, I'll show you guys in just a second. It's underneath Sites, EGI Support, Document Library, and then Virtual Training. And now keep in mind that if everybody is loading in the same, so this is a collaboration tool. So anybody who uploads to this location, so this virtual training location, will be able to access the files. So just keep that in mind when you're saving your file there, that you want to add like a unique name. So in this case, I can call it like NK and then save it. But I just want to make sure that whatever name that I save it to is going to be unique and something that I can identify later on. The other option for where you can save it is if you want to save it to your desktop. If you click the SDK user option, you'll be taken to the SDK11 directory where most of your scenarios are going to be saved. I'm going to create myself a new folder, and I'm going to call this SmallSat Orbit Design. And right now my file is in the VDF format, but that's okay. I can use this dropdown to save it as a scenario. And what that does is that rather than it being packaged up into one item, I can then see all the files that I have then saved in my scenario. All right. And now when I go ahead and save it, it'll always just save to that directory. So this is saving it to my local machine, but of course you can always save it to the SDF as well, and just keep in mind that it's a collaboration tool, so everybody will see the files that are uploaded there. So just remember what you name your file as. All right, so let's go over this scenario that we have just opened up. You'll see here in your object browser that we have a list of volcanoes in our scenario. They're also loaded into their own constellation. So let's take a look at one of these volcanoes. I'm going to let the streaming imagery load in. I'm going to zoom out on the ground just to see what I'm looking at. And I can see all, so in my 2D graphics I can see the markers for all my ground sites, and then in the 3D graphics window I can also see my volcano here, and then the markers for my other ground sites. Now I'm just going to go back to the home view button so I can get a full perspective of my globe. And now, so now that we know where all our volcanoes are going to be, we're going to bring in a satellite. We want our satellite to be able to observe all of these volcanoes that we see here. And we want our satellite's orbit to just like maximize all our observation times. We're going to begin by just bringing in a very generic satellite in a very generic orbit, and then we'll analyze and design the optimal orbit for our mission. So let's just bring in our satellite. I'm going to use the orbit wizard to bring in my satellite. And this dark blue is a little hard to see, so I'm going to just change my color to white to make it a little bit clearer. And I'm going to call this my SDK sat. So I'm just bringing in a very simple orbit. If I do something like show all objects, I can see where my volcanoes are located. But I'm just using the default parameters, so an inclination of 45 degrees, the altitude is going to be 500, RAN is set to 0. So just using those initial parameters, because I just want to at least bring in my objects and my assets and take a look at them. And then I can click OK. We can also open up our properties of our satellite and just take a look at what those parameters are. So remember, we had the altitude set to that 500 kilometers, but the semi-major axis value for that is going to be 6,878.14 kilometers. So if I did want to go back and make any changes or adjust things, I could certainly do so here. When we talked about the scope of our analysis, we mentioned that there were that we were going to ignore the solar radiation pressure, atmospheric effects, lunar gravitation effects, and the higher Earth order of lateness effects. All those parameters and those characteristics are taken into account by the propagator that is being used to model the orbit. So to simplify our mission and to simplify our setup, we're going to be using the J2 perturbation propagator. So if you haven't already, please open up the properties of your satellite and change the propagator to the J2 perturbation model. And then we can go ahead and click OK. So now we see our satellite. Next, let's add in our payload. So I'm going to have us insert in a new sensor. And this sensor will be placed on our STK satellite. We're not going to make any changes to the sensor. We're just going to use the default because our goal for this initial setup is just designing our orbit. And now if I take a look in my 3D graphics window, I should see a ring around where my STK satellite is. And just to show you, if I zoomed to my object, I can see that my payload is has a cone half angle of 45 degrees. Right here. Okay. Great. So now we have all the assets we need in our mission. We have our targets, in this case our volcanoes on the ground, the ones that we are trying to observe and figure out when they could possibly be erupting. We have our satellite that's going to be in orbit and its payload, that sensor. So I'm going to call my sensor Imager. That will be doing the actual observations. So our goal now is to figure out where our satellite should be in orbit so we can maximize the observations of these volcanoes. Before we even begin the analytical part of this, or before we even begin the design portion of this lab, I'm going to have us actually compute what this initial setup is giving us and what our initial data is. So I'm going to have us now bring in a chain object. So a chain object is it's a different type of axis calculation. So rather than it being a one-to-one relationship, you can list your objects in a sequence for the way you want your information to flow. So in this case, let's actually open this up. Let's hit the Define Properties option. And in this case, what we want to know is when our imager can observe any of the volcanoes that we have on the ground. So we're not going to bring in each one individually because that would have to be a specific order. Instead, we're going to just compute access, in this case chain access, to this constellation of volcanoes, which is the grouping of the objects. So now my list and order here does matter. So I want the information to go from my imager, so my imager that is on the satellite, to my volcanoes. And once you have both of those listed on the right, you can go ahead and hit apply and OK and save your scenario, save the scenario where you are. Now, to get a read of this data, a couple things we can do. There's a setting in the chain object that lets you automatically compute. If that was disabled, you can always right-click on the chain object, go to the chain menu, and then hit Compute Axes. And that will compute the axis calculation for your chain object. And once you have that computed, we can open up the Reports and Graph Manager tool. And for the chain object, we can take a look at our complete chain axis. So this report here is going to show me how many times my imager can view any of my volcanoes that are on the ground. So I like to generate this as a report because then I can see the data right in front of me, have it listed out. So let's take a look at what our initial setup is. So with this most basic orbit, in this first column here, I can see the number of axes I have. So this isn't to a specific volcano, this is just to any of the volcanoes. When it comes in view, and then when that ends. And then if I scroll all the way to the bottom, I also see these summary values. So min duration, max duration, and then total. The value in the component we are going to be most interested in is this total duration. We want to maximize the total time our imager can view any of the volcanoes that are on the ground. Now this value here, if you just take a look at your units up at the top, is in seconds. At least for myself, that's not as intuitive as something like hours. And what's great about doing something in SDK and looking at your reports is that these reports are very customizable and you can choose what data you want to see and how you want to see it. So I can also interact with this data too. So if I actually right-click on this value right here, so where I'm seeing that 7,727.94 second value, if I right-click on this value, I get a menu. In that menu option, I have something called Report Units. And I can choose what units I want to see my data. So I have my date format, which is fine, but I have this time. And my time is currently listed in seconds. And I can just use this menu on the right to change my units to hours. And when I hit apply and OK, and then I take a look back down at my report, I can see that this value is no longer in seconds. I'm seeing a value of 2 hours, or 2.147 hours. And this is true for anything in this column. So the report that we used, and if you've gone through the level 1 certification, you know that there are the installed styles, so things that you can't change in SDK, and then the report styles that you change and you can customize. Since we opened up an installed style and we made changes to it, if we wanted to continue using this sort of setup, what we would do is we would save it as a quick report. So up at the top of your report, locate the Save as Quick Report option. It's a little purple notebook with a little lightning bolt and a plus sign. And if you click that, you'll see it now pop up in your list of potential quick reports. So this is my complete chain axis report, but my units are going to be in hours. All right, now that we have an understanding of what our initial setup is going to be, let's get started with designing our orbit. We're going to use a tool called Analyzer for this study. So to open up the Analyzer tool, I'm going to have us go to Analysis, and then in the drop-down, you should see an option called Analyzer. And then there are various options you can use specific to Analyzer. This first option here will open up the tool, and what you see listed down below are the various types of analyses that you can do. All right. So for now, go up to Analysis, use the drop-down, locate Analyzer, and then open up the Analyzer tool. And I'm going to walk us through this window and this panel just so you guys can get an understanding of what you're seeing. So when you open up the Analyzer tool, you'll see a couple things going on in your windows. On the left over here, you'll see all the assets that you have in your analysis and even the calculations. And then in this middle section, you have the variables that you can utilize. So your independent variables, the things you want to change, and then the types of results you want to pull out. And the variables you will select will appear in the list on your right. So for the focus of what we're working on, we're going to be varying aspects of our satellite. So I'm going to highlight my SDK satellite in my list on the very, very far left. And then I'm going to expand the propagator section. So it says propagator and then J2 perturbation. Recall that we changed the perturbation model for our orbit. And then we can go through and choose which values we want to utilize for the analysis. So in our case, we're going to be approaching the problem in a couple different ways. The first setup that we're going to be talking about and focusing in on is going to be analyzing an ideal circular orbit for our satellite. So say we launch some satellite into orbit and we knew it had to be into some circular orbit. So in that case, we're not going to be changing too much. We'll just be focusing in on the semi-major axis and the inclination. So I'm going to highlight and I'm going to bring over just by double-clicking the semi-major axis and the inclination. So that'll let me do the analysis just with those two parameters. Later on in the study, so then the second part, we'll be taking a look at the effects of having an elliptical orbit. So say we were able to launch our satellite into some elliptical orbit. In that case, we'll actually have some set eccentricity that we're going to utilize, and we're going to set the semi-major axis values. But we're going to also vary the argument of perigee. So in total, we'll be looking at 4 parameters. And I don't have to redo the experiment by coming back to this page and loading the variables that I want over and over again. I can actually just select the ones I want to use right now, and then when I actually am doing the analysis, I can choose which parameters I want to change, which ones I want to keep the same, and don't worry, we'll walk through all of that. Just note that for the time being, I'm going to have us all bring in these 4 orbital parameters. So that's semi-major axis, inclination, eccentricity, and then argument of perigee. Now the next thing we want to talk about is what our results are going to be and what data we are specifically interested in. So we brought in our chain object. Recall that we also generated the data, and we wanted to look at the total chain axis duration. So I'm going to highlight my chain object, and then I'm going to go down to this data provider variables list. And you might see it says no data providers listed. Don't worry about that. Down below, there's a little checkbox that says show all data providers. And I'm going to enable that to see the complete list of data providers for my chain object. So for this chain object, I highlighted it on the left. In the middle panel, I just enabled this show all data providers. And now to actually choose the data I want to utilize, I'm going to locate the complete access directory, and open that up. I see now that I have something called axis number, start time, stop time, and then duration. And the value that I am most interested in is going to be the duration sum. So that is going to be the total time my imager can see any of the volcanoes that are on the ground. And I'm going to double click on that to bring it over on the right. And so now looking at my analyzer variables, I have 4 inputs and then 1 output. So just make sure you have your variables in there. And the type of analysis we're going to do with Analyzer is going to be called a design of experiments. So this is a capability built in with an analyzer that lets you choose how many variables you want to use, any number of it, and then choose the type of algorithm you want to use to solve it as well. You'll also notice up here there's different types of analysis functions. So a parametric study is when you vary 1 parameter, see 1 result. Carpet plot, you vary 2, and then see your result. And then design of experiment, you can have X number of variables and X number of results. And then we also have optimization tools, probabilistic tools, and then you can see all of those if you just hover over the names over here. You can also script in various macros if you want to automate any of your analysis steps. All right, for our study, we're going to focus in on the design of experiments. So I'm going to open up that capability by clicking the little cube icon. In my design of experiments tool on the left, I'm going to see the variables that I brought over, so semi-major axis, inclination, blah, blah, and so on. My results, so my complete chain axis duration. And then on the right, I see design variables and then responses. So what I'm going to do is I'm going to drag and drop my variables over onto the right so that I can use them in the analysis. So we're only going to be bringing in the semi-major axis and the inclination. So we're going to save the eccentricity and the argument of perigee for later. But what's really neat about doing this in Analyzer is, so you'll see that the eccentricity is like nearly 0. You know, it's e to the negative 15. So if I wanted to write in 0 and then do something like sync to SDK, you know, I could do that there. And it'll also update the duration sum down here. But if I change any of my values that I see listed here, I can always click that Sync to SDK button and just load my setup, the one that I have on this panel on the left, and then load it into SDK. So that's really neat. And I'm just going to move my windows off to the side to make it a little bit easier to view. And now I'm going to bring over my parameters. So I'm going to bring over my semi-major axis by just dragging and dropping, and I'm going to bring over my inclination. So now I can see that I have some high and low values that I can use, and I can actually, clarify it a little bit more, and I can use the drop-down and set my values to low, high, and then levels. And this lets me choose my min value, my max value, and then also the number of steps I want to take. So for our study, we knew that we had some requirements, that we needed our semi-major axis to be between some certain values. So our low value, I'm going to have us set that to 6,628. Our high value is going to be 6,928. And the number of levels we're going to do is going to be 3. Oh, and I guess I didn't point out, but if you look down here, I think it started off saying full factorial, but as you build in the mission, it'll choose a design for you to utilize, and of course, if you don't want to use it, you can use a different one. All right. We also said we were going to restrict our inclination between 0 and 90 degrees, and the number of levels we're going to do are going to be 10. So we're going to have, in total, 30 unique setups for our analysis. So 30 runs right here. And now if you're curious about what values you're actually stepping to, you can click this tab that says Design Table and see that we are going between our three different semi-major axis values and then all those different inclination values that we could do. So I'm going to go ahead and click Run. And what I do recommend is if you want to move this panel off to the side when you hit Run, what you can see is how your system will change in your STK scenario. So that's something else you can keep an eye on. So I'm going to go ahead and run, and then I'm going to pull this off to the side so you guys can see it animate on my screen. Oh, and of course, most importantly, before you even run this mission, you want to make sure you choose a response or a potential result. So the final thing that you want to do is you want to take your sum and you want to just drag and drop it into the response tabs. So it'll use these various setups up here, and for each one, it'll calculate an updated duration sum value. So I can see that as my calculation goes through its various 30 iterations, my semi-major axis is changing, which I can see easier on my 3D graphics. And then my inclination is also changing as well, which you can see, I think, a little bit easier on the 2D graphics panel. All right, looks like my analysis is complete. So this was the setup that I had, but now you should also have a little phoenix icon down below, and you'll see the full and complete analysis that was just run. So what I'm seeing on this table here is the my semi-major axis value, my inclination, and then that third row is the corresponding sum value. So it looks like there's definitely inclinations where, I certainly cannot see what's going on with my volcanoes. Now looking at the table this way is, I can see it, I can understand it, but I can look at it in more intuitive formats. So up at the top, I'm going to click Add View, and I'm going to open up a 3D scatter plot. So my axes in this situation, I have my inclination off to this side, semi-major axis off to this side, and then my sum. So the values that I want to maximize are this sum. And what's also nice is I can, move around this display to understand what's going on with all these points. So looking at it from this angle, I see all my inclination value, or my semi-major axis values. Turning it this way, you can see all my inclination values. So looking at this and just sort of moving it around, I can see that my higher semi-major axis value looks to be, a really good setup. So I'll probably stick with that. And now for my inclination, I see a sort of peak going on at the 60 degrees. However, I know that doesn't appear to be symmetrical, so maybe there is a better inclination for me to utilize for my setup. So looking at this, I can see that my highest semi-major axis is definitely maximizing my data. And then looking at this table over here, it's not clear to me as to what inclination I should have my satellite at. So I'm going to actually rerun my setup, but this time I'm going to focus in on maximizing my inclination. So you can save this result if you would like to. And if you wanted to remember where you saved your scenario, it would have been in your STK11 directory or into your VDF. So you can just go ahead and save your study. So I'm going to bring back my window. So I have two monitors right now, so I just pulled off to the side. And I want to bring over not just my analyzer tool, but this DOE tool, my design of experiment tool. So now that I've run through my setup, I know that my maximized semi-major axis is the one that can help me get to the highest orbit. So I'm going to set my value here. So I'm going to write 6928. and I'll sync to SDK. I'm going to remove my semi-major axis from my design variables list now, because I'm no longer going to use it for my study. But I'm going to leave my inclination there, because I saw from my data that there was some sort of peak. I'm just not clear as to when that peak was. So in my setup, I saw that it maximized around 60 degrees. So I'm going to go ahead and I'm going to set my low value to, saying 55, and then my high value of 65, and run 11 levels actually. So it's going to be inclusive. So if you look at the design table, you'll see that I'm going to be iterating through 55, 56, 57, and so on. So what I'm trying to do is figure out what is the actual best inclination for me to use in the setup. I saw earlier that there was a peak at 60 degrees, but I'm not entirely sure as to where it was. So I'm just going to focus in around that peak point that I saw in my graph, and then rerun this analysis to take a look at my results. So now I'm going to go ahead and hit run. And I'll once again just move some of these things out of the way, so you guys can hopefully see the data, but I think it would run really fast. Fantastic. All right, so I'm going to pull up my data. So in my second trait study that I just ran, I am now varying between an inclination of 55 degrees and 65 degrees. And I can see my data in my table over here. And let's just try to visualize this. So now I'm going to generate a 2D line plot. So 2D because right now I don't have a third variable. I was just looking at the effects of the inclination. So looking at my data here, initially I thought I had a peak at 60 degrees, but now that I fine-tuned this, and now I'm going from 55 to 65, I see that a better value for me is at 57 degrees. So that's good to know. And now I can actually use this for the for my orbit setup. So I'm going to bring back my DOE tool, and now I'm going to go ahead and type in 57 for my inclination, and I'm going to click Sync to STK. So now I'm not running the analysis, I just set my parameters over here, and I clicked Sync to STK. If you wanted to check what this was doing, and I'll just pull this off to the side, but if I open up my satellite's properties, I can see that the values that I set, so my 57 and my semi-major axis, are now loaded in. So if I actually open up my quick report for the complete chain access, I'll now see what my max duration is for that particular orbit. So now I was able to maximize my orbit. Initially I had some value of like 2 hours and some minutes, like 2.14 whatever, but now I can see that I've maximized this for a circular orbit, so that I now have 6.664 hours of total observation time for any of the volcanoes on the ground. Another great way to view this data is also down by viewing it in our timeline view. So I'm going to open up my timeline view, which right now is being minimized, but you can actually go in and show your data in your timeline view underneath your chain object. I might do that at the end so that I'm not cluttering up my view, but don't worry, I'll show you guys that once we're done with our setup. Right. So now using this tool, we have designed a orbit that fulfills the criteria that we had set up. So to summarize, we varied the semi-major axis and the inclination. Just looking at the ideal circular orbit that we could utilize. But now let's look at the effects of eccentricity. And we'll now look at an elliptical orbit for our satellite. So our assumption in this next setup is that the most eccentric orbit is going to be allowed. And here, I'll just bring this up really quickly. So taking a look at our equation for eccentricity, and with the altitude ranges that we have, recall that we have some boundaries for our Cubesat, the limits of which are that 250 kilometers and then 550 kilometers, so still low Earth. So using these criteria, we can determine that the most eccentric orbit that is possible is one that has an eccentricity of 0.0221. And now with this eccentricity and with our radius of perigee and apogee limits, so if this is our perigee and then our apogee, we can also calculate what the semi-major axis is going to be for that orbit. So using these as our perigee and apogee limits, we can calculate and find that our semi-major axis for this orbit is going to be 6,778 kilometers. And so now we can actually load these values into Analyzer, and this allows us to assume the most eccentric orbit, and then use these values in the calculation. So let me just bring back my design of experiment tool. So now I'm no longer going to vary my inclination. I'm going to just bring that out. I'm just going to click delete on my computer, and that works. And like we saw from the slide, we now know that the ideal eccentric orbit for us, or the most eccentric orbit that we can utilize, is going to be one of a value of 0.0221. And now we also want to update our semi-major axis. So recall that this one that we currently have written in there is one that we brought in for a circular orbit, but we used those as our perigee and apogee limits, so the boundaries that we had. So up at the top where it says semi-major axis, I'm going to write in 6,778, and the units are kilometers. So now if you want to take a look at your setup, just know that, so we're leaving the inclination as the 57 that we calculated before, but we're just updating the semi-major axis and the eccentricity to give us some eccentric orbit. And if you wanted to always double check, in case you didn't know, if you hit the Sync to STK button, you can go back into the table and just make sure your values are there. Right. So we're not going to be varying the semi-major axis or the eccentricity because we got those from our equations, and we're going to keep our same inclination values that we calculated earlier. So for this part, we're going to be focusing in on what the optimal argument of perigee would be for our analysis. So I'm going to now drag and drop my argument of perigee, and I'm going to let us explore the entire possible regime for this part. So I'm going to have my low value be 0. I'm going to have my high set to 360, so 0 to 360 degrees. And recall that it's going to be inclusive. So I'm going to use a step size of 10. So I'm going to have 37 total levels. And then also make sure that your duration sum is down below at the bottom of your table. So taking a look at my design table right now, I can see that I'm going from 0 to 360 in steps of 10. So once you have these values in there, you can go ahead and click Run. And then I'll move these aside so you guys can see any of the changes that appear on my screen. So you're seeing the satellite. I think it's easier to see in the 2D graphics window. All the various argument of perigee values that can be utilized. It looks like my analysis is complete. So I have a new table to look at for my values. And I can see all the various argument of perigee points and then all the possible results. So I'm going to once again generate a 2D line plot. And now I'm going to take a look at my data from this specific run. Alright, so I can see sort of like a sinusoidal pattern here, and it looks like my I can maximize my duration, so my observation time, when my argument of perigee is 250 degrees. Although, it's not entirely clear if that is in fact the optimal location. So just like what we did with the inclination, let's fine-tune this study and just focus in on figuring out if 250 degrees for our argument of perigee is really the best, or if there is another value that should be better. And, looking at this peak over here, so I have 240 and then 260. These are all pretty, it's spread out, but it's all sort of pretty close. So I'm going to actually have my range be from 240 to 260, and then we'll take a look at those results. So I'm going to bring back my design of experiments tool, and I'm going to set my low value to 240, my high value to 260, and set this to have 21 levels. And then if we want to check our design table, you can see that we're taking steps of 1. So I'm just focusing in on that peak that I sort of saw that wasn't entirely clear as to when it was. I'm going to go ahead and click Run. And just to reiterate, as you can see, when we're running Analyzer, and I can pull up the table just to show you, Analyzer is pushing the various parameters into SDK and running the same analysis. So just to be clear as to what you're seeing when you're looking at my screen over here, it's not only just moving the orbit and showing you where it can be, it's also going through that computation and showing you what the results should be. Alright, great. So now it looks like our analysis is done. So let's just take a look at our data again. So I'm going to generate a 2D line plot. Alright, so it looks like I'm going from 240 to 260. And it actually looks like my data, so initially I thought I was around 250. Now it looks like my peak is actually at an argument of perigee of 255 degrees. So I can use this value and just put it back into my design of experiments window. So argument of perigee, I'm going to rate it 255 and then sync to SDK. So syncing to SDK, I'm now once again pushing the setup that I have put in over here. So I wrote in my values and then I hit sync to SDK to take these values and then push them into SDK and model them. And if I go back and actually reopen my complete chain access, I can see now that with an elliptical orbit, I have an additional 0.2 hours of observation times. So with my circular orbit, my value of observation times was 6 hours, 6.664 hours. And now I can see that with an elliptical orbit, I have added on some additional observation times. And if you're curious about what this data is, let me also show you some of our data providers. So you can see which value it was that we were focusing in on for this study. So another important aspect of doing a sort of this type of mission where you're designing your setup, your orbit, your mission, whatever, It's always good to understand what it is, what data it is that you are interested in. So in my object, in my report and graph manager, I'm going to change my object type to chain. And I'm going to open up the complete chain access reports properties. So the way to do that is you can right click on it and then hit properties, and notice that that icon of that little yellow like notepad is also up at the top too. I'm going to move this off to the side and make this window a little bit bigger. All right, so my complete chain access duration. So just like you saw in Analyzer, when we were choosing our variables, we went to the complete access and then duration. And so you can see here that this was the value that we were specifically calculating on in Analyzer. So bringing this back here, so for underneath my complete chain access duration, this is the value I was most interested in. And then, of course, when we were looking at Analyzer, we had options of looking at the min, max, average, and then, in our case, we were looking at the sum. All right, so I'm going to go ahead and close this out. I'm not going to make any changes. But if you did want to go back to take a look at the report, that is now saved for ours. Remember, we saved that in as a quick report so that we could easily regenerate our data and just see what our value is going to be for our new orbit. All right, since we're done with our trait analysis and we have set our final values into our orbit, so just to show you again, I'm going to open up my satellite's properties and show you that this is for my elliptical orbit. I have my semi-major axis value that I used my equations to calculate for, as well as my eccentricity. I have my inclination that was calculated earlier in our mission, and then in our latest run of our trait analysis, we figured out what the optimal argument of perigee would be. So we ran this trait study using Analyzer, but you can also do this with some external tools or scripts. So the other example we have of doing this lab is using MATLAB, but of course if you have other tools like Python or any other language, you can use that tool to also solve your problems. I'm going to quickly bring up this slide here just so you guys can see what the final values were for our mission. So we found what the ideal, so I guess just to take a step back, to summarize, when we began this study, we had a starter scenario. So in your case, it might be, the beginning aspects of whatever mission it is you're working on. In our case, we had a set of volcanoes we wanted to observe, and we had a constellation object that had all of those ground sites listed in. We brought in our satellite with an imager. We computed a chain access. And then with the Analyzer tool, we were able to vary the orbital elements of our SDK sat, and we're able to determine the optimal orbit so we can maximize the axis duration to the volcanoes we wanted to image, so the volcanoes on the ground. So that meant that in our case, we figured out what the ideal circular orbit could be, and we figured that out by varying the semi-major axis and the inclination. And then we also considered the effects of if we were able to have the most eccentric orbit, what would our data look like? And so we calculated the eccentricity. We set a fixed semi-major axis inclination and eccentricity, and then calculated what the argument of perigee could be. And now, so now we know what orbits we would need to maximize the amount of time to image any of our volcanoes on the ground. And that way we can collect the most information about, in the situation, all volcanoes in the US. I hope this was a good introduction to designing and optimizing an orbit in SDK using Analyzer. Just keep in mind that this was a pretty simple example because we didn't consider the additional forces or realistic environmental effects. However, since we have built all of this in SDK, we can certainly go back in and then add that next level of fidelity into our analysis. So this was the first part of our SmallSat series, and Like I said, this week we were just focusing in on orbit design. Next week we'll be taking a look at solar and power design, so taking a look at how much energy our small sat can calculate and its solar panels can generate. And then our final topic will be covering communication design. I highly recommend that if you attended this event that you check out our next two. They sort of build up upon each other, and don't worry, we'll provide you all the scenarios that you might need. Part 2 and part 3 will build upon this scenario that we built today, and then we'll provide you guys with any other scenarios that you might need so that you can dive right into that topic. So I hope you enjoyed today's session, and I will see you guys in our next session.